Welcome to Me22088 Vibration and Noise Control. Today we are diving into Unit 2, specifically focusing on the forced vibration. This unit is crucial for understanding how external forces impact mechanical systems and how we can control those vibrations. This course is led by Dr. C. Sandamarikannan, Associate Professor in the Department of Mechanical Engineering at SVC. In this unit, we will be exploring the fundamental concepts of forced vibration through these illustrative diagrams. Let's begin by examining what this figures and corresponding forced vibration concepts. Let's take a moment to look at the roadmap for our discussion today. This outline will give you a clear picture of the topics we will be covering in this chapter. We will begin with a brief introduction, setting the stage for the concepts we will be exploring. Next, we will be delve into the equation of motion, which is mathematical foundation for understanding how systems respond to forces. From there, we will be examining the response of an undamped system under harmonic force. This will help us understand the fundamental behavior of systems without damping. Then we will move on to the more realistic scenario of a damped system under harmonic force, exploring how damping affects the system's response. We will further investigate the response of a damped system under exponential forced vibrations, that is, it is in the form of sine wave or cosine wave. It is a specific type of harmonic force representing the many crucial applications. Finally, we will wrap up by discussing the forced vibration response of the two degree of freedom systems. This structured approach will ensure that we will get a strong understanding of forced vibration, progressing from simpler concepts to more complex ones. So let's dive right into our introduction. Alright, let's begin. As you can see, force vibrations occur when external energy is supplied to the system while it is vibrating. Think of it like pushing a spring. You are adding energy to keep it moving. The external force can come in various forms. It could be an applied force, like physically pushing or pulling the system, or it could be an imposed displacement excitation, where the base or support of the system is moving. And these forces can be harmonic, like a smooth repeating wave, or non-harmonic, but it is periodic, meaning they repeat but are not smooth waves, non-periodic, which means they don't repeat at all, even random in nature. When a system responds to harmonic excitations, we get harmonic response. This means the system vibrates at the same frequency as the force applied to it. At last, we have transient response. This is what happens when a dynamic system is subjected to suddenly upload to a non-repeating force. Imagine hitting a drum. The initial sound and vibrations are transient response. So, in essence, the forced vibration is about how systems react when we introduce external energy, and understanding different types of forces and responses is very crucial to mastering this topic. Let's move on to a specific scenario, the response of an undamped system under a harmonic force. Here, this damping will be removed. Now we are going for a undamped system. This is very fundamental case that help us understand the basic behavior of vibrating system. Imagine we have a system without damping. no friction or resistance to slow down. And we are applying a harmonic force, which we can represent it as f of t equal to f naught cos omega t, where f naught is the amplitude, omega is the frequency. This force acts on the mass m of the system. The equation of motion for the system is then mx double dot plus kx equal to f naught cos omega t. What is this? This mx double dot represents mass time its acceleration, which is related to inertia of the system, where kx represents restoring force from the spring, where k is the stiffness and x is the displacement. And f naught cos omega t is nothing but external force, that is the harmonic one, which we are applying to the system. Now the homogeneous solution to this equation, the solution without considering the external force, may be like this. It is nothing but x of t is c1 cos omega n t plus c2 sin omega n t, which we already discussed during the free vibration system without damping. And we know that the natural frequency is given by omega equal to root of square root of k by m. This is the frequency at which the system would vibrate if there were no external force and no damping. Understanding this homogeneous solution is very crucial because it forms the basis for finding the complete solution when we consider an external harmonic force. Let me see the steps involved in it and how to get the response for the forced vibration. Building on what we just discussed, let's now find the particular solution and the total response of our undamped system under harmonic force. Since the exciting force and the particular solution are both harmonic and have the same frequency, we can assume a solution that it is x of t equal to x cos omega t, where x represents maximum amplitude of the response, and we can find x, that is the maximum amplitude, using this equation. Let's break down what it is. F naught is the amplitude of the external force, k is the spring stiffness, m is the mass, omega is the frequency of the external force. If we substitute the static deflection, that is F naught by k, the, the same equation can be rewritten like this. It is form which helps us to see how the amplitude of the particular solution depends upon the ratio of forcing frequency omega to the natural frequency omega n. Thus, the solution for this type of system will be given in this, that is C1 cos omega n t plus C2 sin omega n t plus f of divided by km omega square cos omega t. This equation gives us the complete picture of how the undamped system responds to the harmonic force. This includes both the natural vibration of the system and the forced vibration of the system. Now, let's look at how initial conditions influence the response of our undamped system under a harmonic force. To determine the specific values of C1 and C2 in our general solution, that is given in the last slide, we need to consider initial conditions of the system. These are typically the initial displacement and initial velocity. Using the initial displacement x naught and initial velocity x dot, we can find that C1 and C2. These values are then substituted back into our general solution. Thus, we will get the complete expression for response of the harmonic force. As you can see, initial solutions directly affect the coefficients of homogeneous solutions, which represents natural vibration of the systems. Let's consider the maximum amplitude of the forced vibration. We can express this in terms of the static deflection. The ratio of the maximum amplitude to the static deflection is given by 1 divided by 1 minus omega by omega and the whole square. This is the ratio of forcing frequency to the natural frequency. Understanding how these initial conditions and frequency ratio affect the system's response is crucial for analyzing and predicting the behavior of undamped systems under harmonic forces. Now, let's delve deeper into understanding the behavior of our underdamped system under a harmonic force by introducing the concept of the magnification factor. The quantity x divided by del static is called the magnification factor or amplification factor or amplitude ratio. It essentially tells us how much the amplitude of the forced vibration is amplified compared to the static deflection. The variation of this amplitude ratio with the frequency ratio is given in this graph. Let's take a closer look on it. Horizontal axis represents frequency ratio, vertical axis represents magnification ratio. As you can see, the graph shows significant change in the magnification factor as the frequency ratio changes. Based on this graph, we can identify three distinct types of responses. That is, we can see it in the next slide. Let's look at the three distinct cases, case by case. The first case is given here. This case focuses on the frequency ratio omega by omega n is between 0 and 1. In other words, the forcing frequency omega is less than the natural frequency. Then this condition is going to be there. The denominator in the equation of the magnification factor is positive. That is, if omega is going to be lesser than omega n, this the value, entire value will become positive. That is, magnification factor is positive. The response of the system is given without any change. This means there is no phase shift between the applied force and the system's response. You can see it in the diagram. The system response is starting as such where the harmonic force is there. The peak and troughs of both graphs align perfectly. This shows that the harmonic response of the system is in phase with the external force. The system's displacement follows the same pattern as the force applied to it. Let's move on to case 2 where we explore the system behavior when the forcing frequency omega is greater than natural frequency. This means the frequency ratio is greater than 1. In this scenario, the denominator in the equation will become negative. The equation for the amplitude now look like this. Notice that the denominator is rearranged to ensure we are dealing with a positive value for the amplitude x. Because the denominator is negative, steady state solution can be expressed in terms of negative sign. Here it is very crucial. It indicates a phase shift of 180 between the applied force and the system's response. Let's look at the graph to visualize the phase difference. Top graph shows the applied force f of t. The bottom graph shows the system's response. Notice how the peak of the response graph align with the trough of the force graph and vice versa. This demonstrates 180-degree phase shift. So, when the frequency ratio is greater than 1, the system's harmonic response is out of phase with the external force. As you can see, the variation in the response are clearly shown in the figure, illustrating the impact of the frequency ratio on the phase relationship between the force and the system's displacement. Now, we come to the crucial and most important destructive scenario, that is case 3, which is resonance. This occurs when the forcing frequency is equal to natural frequency. In other words, frequency ratio is exactly 1. When the frequency ratio is exactly 1, denominator in our equation for the amplitude x became 0. As a result, the amplitude x became infinite. In a real world system, of course, the amplitude won't literally become infinite, but it will become very large. This condition where the forcing frequency matches the natural frequency is called resonance. It is a fundamental concept in vibration analysis, and it is crucial to understand because it can lead to catastrophic failures in structures and machines. Let's look at this graph to understand what happens during resonance. The graph shows system's response over a period of time. Notice how the amplitude of oscillation increases linearly with respect to time. This is a hallmark of resonance. The system is continuously gaining energy from the external force, leading to larger and larger vibrations. Then the total response for this kind of system, that is at resonance, is represented by this equation. The key term is the last term. The presence of term T indicates the linear growth of the amplitude over a period of time. To reiterate, the resonance occurs when forcing frequency is equal to the natural frequency. This condition must be avoided in many engineering applications to prevent excessive vibrations and potential failures. This is very much crucial to design the systems that can able to withstand vibrations and to avoid catastrophic failures. Now, let's take a look at the total response of the system when frequency ratio is less than 1, which we discussed as case 1. The total response x of t can be represented like this. Here, what is the meaning of this solution? This term represents homogeneous solutions, which is the natural vibration of the system. A is the amplitude, omega n is the natural frequency, phi is the phase angle determined by the initial conditions. The second term represents particularly the solution, which is the forced vibration due to external harmonic force, where del static is the static deflection, omega is the forcing frequency, and the term denominator is the magnification factor we discussed earlier. The graph illustrates this total response. That is, the horizontal axis represents time, the vertical axis represents the displacement. The graph shows combination of two sinusoidal waves. Higher frequency wave represents forced vibration with frequency omega. Its amplitude is given by this form and it is integrated in the graph. The lower frequency wave represents natural vibration with frequency omega n, it is amplitude A. The total response of the system is sum of these two waves, resulting in a complex waveform that shows the combined effect of the natural and forced vibrations. Remember, this specific form of the total response is valid only when the frequency ratio that is less than 1. In this case, the forced vibration is in phase with the external force and the total response shows a combination of the natural and forced vibrations. Now, let's tackle a practical problem involving forced vibration. We have a scenario where reciprocating pump is mounted on a steel plate and we need to determine the amplitude of vibration of this plate. As you can see in this image, a reciprocating pump with a mass of 75 kg is mounted at the center of a steel plate. The plate has the following dimensions: thickness 13 millimeters, width 500 millimeter, length 2.5 meters. This plate is clamped along two edges, creating a specific boundary condition, that is fixed to fixed beam. During the operation of the pump, the plate is subjected to continuous harmonic force represented by the equation 250 cos 62.80 N, where 250 is Newton, 250 is the amplitude of the force, the unit is Newton, and 62.8 is the frequency of the force, which is omega radians per second. Our objective is to find the amplitude of vibration of the moving plate. This involves analyzing the system response to the given harmonic force, considering the plate's physical properties and boundary conditions. To solve this problem, we will need to apply our understanding of forced vibration, particularly the concepts of natural frequency, forced frequency, and the resulting amplitude of vibration. We will proceed step by step to determine the solution. Now, let's proceed with the solution to determine amplitude of vibration of this plate. First, we model the plate as a fixed beam. It is reasonable assumption given that the plate is clamped along two edges. This model allows us to use beam bending theory to determine the plate stiffness. We are given the following properties, that is Young's modulus is 200 gigapascals. This represents material stiffness. Length 2.5 meters. Area moment of inertia. We need to calculate this. The formula for area moment of inertia is 1 by 12 width into thickness cube. This is width, this is thickness. So plugging the given values, we will get that it is moment of inertia, that is area moment of inertia is 9.2 into 10 power minus 8 meter to the power of 4. The bending stiffness of the beam is given by this formula is specific to fixed beam. Let's plug in the given values and calculating this, we will get stiffness value as 2 to 6.1 kilonewton per meter. This represents stiffness of the plate, which is crucial for determining vibration response. We have now determined the bending stiffness of the plate. In the next step, we will use this value to calculate natural frequency of the system. Now, let's complete the solution by calculating the amplitude of vibration x. The equation we use is x equal to f naught divided by k minus m omega square, since there is no damping. This equation relates the amplitude of x to the amplitude of force bending stiffness, and forcing frequency. Let's we substitute the values what we have in the question, that is F naught value is 250 Newton, and we calculated stiffness and omega. Let me substitute all these values. We will get the x, the amplitude of this plate supporting a pump is given as 3.57 meters. That is, it is 3.57 millimeters. The negative sign indicates that the displacement is 180-degree out of phase with the applied force. In terms of amplitude of vibration, we interested in the magnitude value only. That is, it is 3.57 millimeters. Therefore, the amplitude of vibration of the plate supporting the pump is 3.57 millimeters. This completes the solution to our problem. All right, we have explored the behavior of an undamped system under an harmonic force. Now, let's move on to a more realistic scenario, the response of a damped system under harmonic force. As you can see in the diagrams, we now have a damping element represented by C in addition to the mass and spring. The damping force Cx dot, that is velocity, introduces energy dissipation in the system. The equation of motion for this damped system can be derived as this x equal to f naught cos omega t, where what is the meaning of this equation? X is the amplitude of steady state response, k is the spring stiffness, m is the mass, omega is the forcing frequency, and phi is the phase angle between the response and the force. C is the damping coefficient, and F naught is the amplitude of the external force. Using trigonometric relationships, we can separate these equations into two parts, like such a way that the equation allows us to solve for amplitude x and the phase angle. Hence, we got these two equations number 2 and 3. The solution of this will be x equal to f naught by this, and phase angle pi is tan inverse of this. These two equations are very much crucial for understanding how damping affects the system response. The amplitude x now depends on the damping coefficient C. Phase angle phi is no longer 0 or 180 as in the undamped case. We will have different phase angles. We will delve deeper into the implication of this equation, first equation amplitude, and later we will go for phase angle phi. Now, let's visualize the relationship between the forcing frequency and the steady state response in a damped system using both the graphical and vectorial approach. As stated, the figure shows typical plots of the forcing function and steady state response. Let's start with the graphical representation. The solid line represents the forcing function f of t, which can assume a sinusoidal wave. The dashed line represents steady state response. Notice it is also a sinusoidal wave, but it is shifted in phase compared to the forcing function. The phase shift, the phase shift between the forcing function and the response is denoted by phi. This phase shift is direct result of the damping in the system. The circular diagram on the left further illustrates the phase relationship. The vector rotates counterclockwise with angular velocity omega. the angle between f of t and the response x is the phase angle. Now let's look at the vectorial representation on the right. F naught represent forcing function, capital X represents steady state response, the angle between F naught and X is the phase angle, the vector Kx represents spring force which is in phase with the displacement, the vector m omega square x represents inertia force which is 180-degree out of phase with the displacement, the vector c omega x represents damping force, and it is 90-degree out of phase with the displacement. This diagram clearly shows the force balance in the system. The vector sum of kx m omega square x cwx must equal to the external force F naught for the system to be in steady state. These graphical and vectorial representations help us visualize the phase relationship and the force balance in a damped system under any harmonic excitation. Understanding this representation is very much crucial for analyzing and predicting the behavior of such forced systems. Now, let's simplify the expressions for the magnification factor and phase angle in a damped system using some common substitutions. We will be using the following substitution, that is omega n equal to root of k by m. This is natural frequency of the system. C by m equal to 2 psi omega n. This introduces damping ratio psi which represents level of damping in the system. Del static is static deflection which we have discussed earlier, and R equal to omega by omega n. This is the frequency ratio which is the ratio of the forcing frequency omega to the natural frequency omega n. Substituting all these expressions for the magnification factor, we will get this solution. Now, using the frequency ratio R here, then we can further simplify the response of the system in terms of R. Then, similarly, the phase angle also will be in terms of psi and R. This is the formula to identify and to represent the phase angle between the forced harmonic signal and the response of the system. This simplified expressions for the magnification factor and phase angle are commonly used in vibration analysis. They make it easier to analyze the effect of damping and the frequency ratio on the system response. We will use these expressions to further explore the behavior of damped systems in the next slides. Now, let's analyze the characteristics of the magnification factor denoted as M, which is same as the amplitude ratio x divided by del static in a damped system. The graph shows magnification factor M plotted against the frequency ratio omega by omega n for various values of the damping ratio. Let's observe the key characteristics, that is effect of damping ratio. As you can see, the value of damping significantly affects the shape of and peak of the curves. Low damping, that is psi is less than 1, the curve exhibits a peak at a frequency close to 1, that is R. Frequency ratio omega by omega n is 1. This represents the forcing frequency is equal to the natural frequency, that is resonance, resulting in greater amplification of vibration, the critical damping. Next, move on to psi equal to 1. The system is critically damped. There is no peak here. There is no peak. And magnification gradually decreases as the frequency ratio increases. Overdamping, that is more than 1, that is we are having three scenarios 1.5, 2, and 3. For overdamped system, magnification factor decreases monotonically with increasing frequency ratio. There is no resonance peak. The peak amplitude of the magnification factor decreases as the damping ratio increases. This means that higher damping reduces amplification of vibration even at resonance. Frequency ratio at peak. Frequency ratio at which peak occurs is slightly less than 1 for low damping ratios. As damping ratio increases, the peak becomes less pronounced, shift towards lower frequency ratios. Magnification factor at lower frequency ratios, that is R is less than 1. It approaches 1 for all kind of damping values. This indicates at lower damping, system response is closer to the static deflection. Next thing is at higher frequency ratios, the magnification factor approaches 0 for all damping ratios. This means that at higher frequencies, system's response is significantly reduced. These characteristics highlight the crucial role of damping ratio in controlling the vibration response of a damped system under harmonic excitation. By understanding this relationship, we can design systems to minimize unwanted vibrations and ensure stability. Let's summarize some of the key characteristics what we have observed and discussed. For an undamped system, the magnification factor reduces to infinity or as R approaches 1. This means that in an undamped system, the magnification factor approaches infinity. See, just substitute 1 here, 1 minus 1, it is 0. Since it is 0, x will become infinity. Next thing is, any amount of damping reduces the magnification factor for all values of the forcing frequency. This is very crucial point. And a small amount of damping can significantly reduce the amplitude of vibration, especially near resonance. For any specified value of R, higher value of damping reduces the value of M. This means that increasing the damping in a system will always result in a lower magnification factor, regardless of the forcing frequency. In the degenerate case of a constant force when R equal to 0, the value of M equal to 1. This means that when the forcing frequency is 0, the magnification factor is 1 and the system response is simply the static deflection. These 4 points summarize the key effects of damping on the magnification factors. The next slide, we conclude the characteristics. Let's continue with the remaining key characteristics. The reduction in M in the presence of damping is very significant at or rear resonance. We already seen in the graph, the amplitude of forced vibration becomes smaller and smaller with increasing values of the forcing frequency. This means that the frequency ratio R increases beyond 1, the magnification factor decreases, indicating a reduction in the amplitude of vibration. Note that the statement M tends to infinity when R tends to 1. Very important. Next thing is when the psi value is between 0 to 1 by root of 2. This is very important point that understanding the location of peak amplitude in a damped system. For damping ratio within this specified range, the maximum magnification factor occurs at a frequency ratio slightly less than 1. The frequency is also lower than both undamped natural frequency and damped natural frequency values. These characteristics further emphasize the importance of damping in controlling the vibration of a system. Some other important points is specific characteristics of the magnification factor. The maximum value of x, which we discussed earlier, is given by x by del static equal to 1 by 2 psi root of 1 minus psi square. This equation tells us the maximum amplitude of vibration in terms of damping ratio, and the value of x at forcing frequency equal to natural frequency is given by this terms. This equation shows the amplitude of vibration specifically at the natural frequency. For psi equal to 1 by square root of 2, this means for these specific conditions, the damping ratio is 1 by square root of 2. The slope of the magnification factor curve is 0. In other words, the curve is flat at the origin. For this damping ratio greater than 1 by root 2, there is no peak curve. Then what is the meaning? The magnification factor monotonically decreases with increasing values of R. Now let's turn our attention to the phase angle, which represents the phase difference between the forcing function and the steady state response in a system. The graph shows phase angle plotted against the frequency ratio for various values of the damping ratio. Let's observe the key characteristics. The undamped system, that is psi equal to 0, when R is less than 1, the psi equal to 0 degrees, which is in phase. When R is greater than 1, psi equal to 180 degree, out of phase. At resonance R equal to 1, there is an abrupt jump from 0 degree to 180 degree. The effect of damping ratios: as the damping ratio increases from 0 to some value, even 5, what will happen? For smaller values of damping, the phase angle changes rapidly around R equal to 1. Largest values of psi, the phase angle changes more gradual. Phase angle at lower frequencies, at very low frequency ratios, the phase angle approaches 0 degree for all damping ratios. This means the response is nearly in phase with the forcing frequency. When it is at higher frequencies, at very high frequency ratios, the phase angle approaches 180 degree for all damping ratios. This means the response is nearly out of phase. The phase angle at resonance at R equal to 1, the phase angle is 90 degree for all damping ratios. This means response lags the forcing function by 90 degree. There is a transition region where the phase angle goes from 0 to 180 degree, becomes wider as the damping ratio increases. This indicates that damping smooths out the phase transition. Now, summarize the key aspects of phase angle. behavior in both undamped and damped systems. For an undamped system, shows that the phase angle is 0 degrees when the frequency ratio is between 0 to 1 and 180 degree when R is greater than 1. This means when R is less than 1, the excitation and response are in phase. When R equal to 1, excitation and response are out of phase. This is consistent with what we have seen in previous discussions. However, it is very important that when damping is 0, the phase angle is actually between 0 to 90 degree, implying that the response lacks the excitation. This contradicts the initial statement of being perfectly in phase. This is likely the original means, that is undamped system with R is less than 1, phase angle should be 0 degree. Moving on to damped systems, that is when R equal to greater than 1, the phase angle is given by 90 to 180 degree, implying that response leads the excitation. There is also likely the response lag the excitation is not leading us in some cases. It is important to note there are very important things, that is when it is damping equal to 0, response lacks the excitation. When damping is greater than 0, response leads the excitation. Similarly, for damping is greater than 1, R equal to 1, phase angle is given by 90 degree, implying that the phase difference between the excitation and the response is 90 degree. For psi is greater than 0 and large values of R, the phase angle approaches 180 degree, implying that the response and excitation are out of phase. For an undamped system, the total response x of t is given by this expression and omega d is given by this expression. The initial conditions are given as x naught equal to x naught cos psi 0 plus x cos psi, and the velocity is given by the expression, which is nothing but the transient response. The exponential term indicates the transient response decays over a period of time. This cos omega phi represents steady state response. To determine specific values of x naught and psi naught, that is response and phase difference, we need to consider the initial conditions of the systems. These are typically initial displacement and initial velocity for the given equations. The equation allows us to solve for x naught and phase angle when we know x naught initial values, initial velocities, amplitude, damping value, forcing frequency, etc. Now we see a problem where we need to find out the total response of a single degree of freedom system under specific two conditions. We have a system with following parameters: mass m is 10 kilograms, damping coefficient C 20 newtons seconds per meter, spring stiffness 4000 newtons per meter, initial displacement 0.01 meter, initial velocity is 0 under these following conditions. That is, an external force F of t is F naught cos omega t acts on the system with omega equal to 10 radians per second. F naught is 100 Newton. This is a case of forced vibration with harmonic force. We need to determine how the system responds to this external force. And also free vibration, if f of t equal to 0, this is free vibration case. When there is no external force acting on the system, we need to determine how the system responds based slowly on the initial condition and its inherent properties like mass, damping, stiffness. To solve this problem, We will need to apply our both understandings based on previous cases, that is free vibration and forced vibration. Here we have to use natural frequency, damping ratio, steady state response, and transient response. We will proceed a step-by-step approach to find total response for this given scenario. Now, let's calculate with the solution. Let's recalculate natural frequency of the system using the formula that is given as 20 radians per second. Then this is the frequency at which the system would oscillate if there were no damping or external force. Next, we calculate static deflection using the forces, that is 100 Newton and 4000 Newton per meter. Substituting these values, we will get del static as 0.025 meter is 25 mm. This is the displacement of the system under static load F naught. Now we calculate damping ratio by substituting C equal to 20 Newton per meter, stiffness 4000 Newton per meter, M equal to 10 kg. We will calculate psi as 0.05, which is, means it is underdamped system. It is less than 1. We calculate the damped natural frequency. Is given as 19.97 radians per second. Then the ratio between forcing frequency and natural frequency, it is 0.5. Now, using all these values, let me calculate the amplitude of the system. The amplitude of the system is going to be, using this separation, we substituting all the very important parameters: static deflection, ratio R, and psi equal to 0.05. We got that the displacement value is 0.0332 meters. Let's continue with the solution. That is, after the amplitude response, we will calculate the phase angle using the phase angle formula. With substituting psi equal to zero point zero 0.05, R equal to zero point 0.5, we will get psi equal to 3.81 degree. Then using the initial conditions, x naught equal to zero point zero 0.01 and the velocity is 0, by this expressions we can able to get, this is giving us this 0.0236, and substituting we will arrive at this two equation. When we solve this, we can able to get the phase angle. Let's continue with the solution and explain. That is, we have the value of x naught cos psi naught from the previous step, and now we will get that x naught sin phi naught is 0.00268. Now substitute both the things, we will get, that is, the maximum amplitude of the vibration using the initial cases, that is the transient response. We will get 0.023297, and we will calculate the phase angle using the this psi naught cos phi and psi naught sin phi. It leads us to 5.58. This is phase angle of the transient response. So we will combine the transient and steady state responses to obtain the total response of the system under post vibration conditions. Let's move on to the second scenario, where we need to find out total response of the system under free vibration, meaning there is no external force. For free vibration, total response x of t is given by this equation 8. This equation represents damped sinusoidal oscillation, where x naught is initial amplitude, psi is damping ratio, omega n is natural frequency, omega d is damped natural frequency, psi naught is the phase angle. Let me calculate x naught. We used the initial conditions and formula. We got x naught as 0.01, naught naught 1, 2. And similarly, we using that initial conditions and substituting it, we will get phase angle for initial free vibration condition is given as minus 0.286 degree. So in this solution, we got for the given problem, that is for free vibration response, by using the initial conditions, we got the amplitude for the free vibration response and the phase angle. This is the complete solution for the given scenario. Let's we go into the very important thing, characteristics of damping and resonance, particularly focusing on low damping values and their impact on system behavior. That is very lesser value instance, it is damping is less than 0.05. We primarily considering the system with low damping, specifically where the damping ratio is less than 0.05. This is important because low damping leads to distinct resonance behavior. First, let's look at the maximum amplitude ratio for low damping. This maximum value occurs approximately when the forcing frequency equals to the natural frequency. That means we will get 1 by 2 psi max. This equation shows for very low damping value, the maximum amplitude ratio becomes very large, indicating significant amplification of vibration at resonance. Next, we have the equation shows that power absorbed by the damper, this is power absorbed by the damper, is proportional to the damping coefficient, forcing frequency and square of the amplitude. Higher damping or larger amplitude result in more power dissipation. Now see the graph. It shows the amplitude ratio is plotted against the frequency ratio. Key features of this graph: peak. A sharp peak occurs at the resonance frequency. A peak value is approximately equal to the quality factor where Q equal to 1 by 2 psi. The bandwidth is defined by the frequencies R1, R2, which are off power points. These are the frequencies at which the amplitude ratio is Q divided by root 2. To find the bandwidth, we find the bandwidth by setting the amplitude ratio. Then the bandwidth will be given as R1 and R2, which defines the bandwidth. The bandwidth is a measure of sharpness of the resonance peak. A narrower bandwidth indicates higher Q factor and a more selective system. In summary, this slide highlights the significant impact of low damping on resonance behavior. Low damping results in high amplitude ratios at resonance, a high Q factor, and a narrow bandwidth. These characteristics are important in various applications. The resonance need to be either enhanced or avoided. We come to our final discussion, that is moving on to complex system, 2 degree of freedom system subjected to forced vibration. As you can see in the diagram, we have two masses M1 and M2 connected by springs K1, K2, K. Harmonic force sin omega t is applied to mass M1. This system has 2 degrees of freedom because each mass can move independently in the horizontal direction. The differential equations of motion for this system can be written as m1 x1 double dot plus k1 plus kx minus kx2 equal to f sin omega t. This equation represents forces acting on mass m1, that is, this m1 x1 double dot is the inertia force, mass times the acceleration, k1 plus k is the restoring force connected to the springs, which is connected to mass m1. Kx2 is the force exerted by the spring connecting both masses m1 and m2. F sin omega t is the external harmonic force. The second equation represents forces acting on mass m2. This equation is similar to the first one, but there is no external force. To solve this equation, we assume the solutions are of the form. These equations represent harmonic oscillations with amplitude A1, A2, same frequency omega as the forcing frequency and common phase angle phi. Substituting this assumed solution into the differential equations of motion and simplifying, we can able to obtain two algebraic equations. These equations can be solved simultaneously to find the amplitudes A1, A2 and phase angle. The phase angle psi can also be determined from these equations or by considering the initial conditions. By solving these equations, we can able to determine response of 2 degree of freedom system to the applied harmonic force. This analysis is crucial for understanding the dynamic behavior of multi-degree of freedom system and designing them to avoid resonance and other undesirable vibrations. Now, let's continue with the solution for the amplitudes A1, A2, which represents the amplitude of vibration for masses M1 and M2. Solving the algebraic equation we derived earlier, we can able to get amplitude expression A1, amplitude expression A2, which is means that amplitude of vibration A1 and A2 becomes infinite when denominators in these equations are zero. This condition is satisfied when the exciting frequency omega is equal to any of the two natural frequencies at the systems. This means that the exciting frequency matches one of the any two natural frequency of the system, therefore resonance will occur. At resonance, amplitudes of vibration becomes theoretically infinity, leading to potentially destructive vibration in real-world systems. A1 becomes 0 when K1 plus K2 equal to M2 omega square. These conditions can be achieved with a specific forcing frequency. In this case, mass M1 became stationary, while mass M2 still has motion. This scenario is possible because mass M1 is initially excited by the external force. Under certain assumption, it can become motionless while mass M2 continues to vibrate. This illustrates the complex dynamic behavior of 2 degree of freedom systems. This analysis highlights the importance of understanding the natural frequency of 2 degree of freedom system and avoiding the resonance. The equations amplitude A1 and A2 provide a way to calculate amplitude of vibrations for different forcing frequencies and different system parameters. By analyzing these equations, we can design systems to minimize unwanted vibrations and to ensure stability. Thank you for joining me today as we explore the fascinating things of force vibrations. Let's recap the key concepts we covered. Undamped systems. We started with undamped systems where we analyzed the response to harmonic forces, including the concept of natural frequency, resonance, magnification factor. We saw how the frequency ratio between the forcing frequency and natural frequency significantly affects the system behavior. Then we moved on to damped systems where we introduced the damping ratio and its impact on the system response and applications. We applied our understanding of forced vibration to solve some practical problems such as determining the amplitude of vibration of a plate supporting a pump. Finally, we extended our analysis to 2 degree of freedom systems where we derived the equations of motions and solved for the amplitude of vibrations. We also discussed the implications of resonance in such systems. I hope this discussion has provided you with a deeper understanding of force vibrations and their significance in various engineering applications. If you have any further questions or would like to explore this topic further, please feel free to contact me using the information provided. Thank you once again for your successful participation. I wish you all the best in your studies and future endeavors.